Следующий гость из Литвы, Donatas. Donatas, представить себя сам.
I will talk in English. I understand Russian, so you can ask questions in Russian, but I don't want to make a presentation in Russian because it would be terrible, because I'm not so good at it, right? So I'm Donatas, and I work as a developer for an online advertising company. And first of all, a short disclaimer here, because this talk is not a hardcore latency talk. I'm not going to talk about CPU caches or whether you should use system.nano time for measuring your latencies and when not. Or I'm also not going to talk about the concurrent data structures like lockless concurrent queues or any magic low latency framework, right? So instead I'm going to talk about how we scaled one of our biggest APIs. Like in 3 years, we went from 500 queries per second to 200,000. And by saying queries per second here, I mean HTTP requests. Yeah. So, and what I'm going to call a low latency here in this presentation. So, by saying low, I mean a request in less than 100 milliseconds. So it could be 1, but if it's 200, it's high, right? And basically, everybody knows that latency is just a size telling us how long something took, like rendering a page or getting a record from a database and so on. Okay, so first of all, let's talk about our business. We show ads, right? Everybody loves ads, right? So basically, the business is simple, but it's hard to scale. So imagine we have a classical ad serving. Yeah, it's not working on a TV. When a user comes to a page, a special script tag is rendered and it requests our ad serving servers, and we return ads and ad is shown. Also, we register the event the ad was shown, and that's it. Then there's real-time bidding stuff. It's more sophisticated serving, which means that when the page loads, a script from some third party is rendered, like Facebook or AppNexus or AdMail, so forth. And that script asks our servers, here's a user, how much would you pay if we show an ad to him? So this is called real-time bidding because we are not the only ones who got that request. And then we return, okay, for that user, if you show him this ad, we would pay like $1, right? And this is sent not only to us, but to our competitors, like in auction, and the highest bid wins, and the ad is shown. Is this clear? Yeah. Okay, so now on the same slide, you can see our architecture of this business. So the real-time bidding API is the API I'm going to talk about. And for load balancing, we use LVSs. It's Linux virtual servers. They work great. They are very low level. Like they can handle 200,000. One server can handle 200,000 keep alive HTTP requests per second. And each server here has about 3,000 HTTP keep alive persistent connections. And we have about 14 servers. So you can imagine it's higher than 100,000 persistent connection. And it's really doing his job great, the Linux virtual server. So for failover, we use Linux keep alive daemon. Anyone uses it in production? Yeah, it works really great. And if one load balancer like this goes down, it automatically switches to this. And at any time, there you can see two data centers. All the load is balanced between them. So for the bidder API, we're using .NET. Don't ask why. It's for historical and legacy systems. But yeah, we use it, and it works for us. For user profiling, we also have some of the APIs written also in .NET, and some of them are written in Scala. For Scala, we use Finagle framework from Twitter, which is very cool framework, a very low-level one. You have a lot of control, and you have many features for high load out of the box, like metrics, like failover and retrying, and so forth. Okay, so when we show an ad, we need to register an event, yeah, right? That the user have seen this ad, and that's. So for user storage, and also for cookie storage, we use Cassandra. Also, for some cases, we use Aerospike, and for content, we use Redis. So for real-time bidding, all the data that needs to be processed, all right, like calculating bid prices for effective bidding, all that stuff is done in Hadoop on Amazon cloud. So, and basically, as I said, there are two data centers, and they always are hot, so they're working all the time. And I think that's pretty much it about the architecture, right? So let's talk about measuring latencies, how we failed in this field, actually. So does anybody knows this page, like the master page of all performance benchmarks for all web frameworks? And can you see something strange here, or like, for example, which one framework would you choose if you know like that average latency is 0.2 milliseconds with a standard deviation 0.5? That means it's twice as bigger as average, right? And when you see a number like this, that maximum could be even 145 milliseconds, meaning it's 500,000 times bigger than the mean, right? So would you choose it? Or would you say that there's something really wrong with these benchmarks, right? Why everybody is measuring latencies in the averages? Because I think that everyone understands it, and it's really easy to calculate. You know, what you need is just a sum of all your latencies and the number of requests. You just divide one from other, and you got an average. But actually, it's a very useless metric, because it can also hide an important or unwanted behavior of the system, like GC pauses, or I don't know, compactions in Cassandra, for example, or other stuff you don't want to know about, because then you'll have to tune something, right? So here's an example why measuring averages is really bad. Like, imagine we have a service with the following response latencies. We've got 20 of them, and these are 5, 7, 8 milliseconds, and so forth. So the average is really easy to calculate. It will be 7.5 milliseconds, right? But what you see here, that 20% of the requests got latency twice as above 10 milliseconds. Imagine your latency requirements are 10 milliseconds. So basically what that means that for 20% of the requests you fail. So I think the percentiles should be the way to go if you want to know really what's happening in your system. Because it shows the maximum or the worst case for the specified part of the request, right? So like for percentile, how to say, 15th percentile would be the max value of 50% of the values. So, and this is basically the formula how to can calculate it. So for our previous example, we just sort all our latencies we recorded, and 15th percentile would be 5, 18th percentile would be 8, 19th 20th, and 99th 25. So you can even have 99.9999, like for example, if you got really strict latency requirements. Is this kind of clear, right? Okay. Yeah, so like percentiles in real life, we don't use averages for measuring latencies. We use percentiles, and 99th percentile is enough for us. So like when you see these spikes, you really start thinking if something is good or wrong with your system. Like when you see such spikes, you think, okay, that's probably garbage collection, and let's tune it, because garbage collection is always fun. And you wouldn't see this in measuring average latencies. There might be some like a bigger steep hill, but you wouldn't notice it in your averages. So don't measure latencies in averages. Some great libraries for tracking latencies in percentiles. The greatest one, I guess, for Java is HDR histogram. It uses fixed memory and constant CPU for recording it and sorting it and figuring out 99th, 5th, and wherever you want, you can configure that. Also, Finagle has built-in the web framework we use from Twitter, and everything is built in, right? Okay, so as I've mentioned in my rest part of the talk, I'm going to talk about the real-time bidding APIs. It's basically an API answering the one simple question, like given a user from Belgium who's interested in sports and culture, how much would you pay if we show an ad for him on, for example, youtube.com? That's simple. API is simple. So don't worry if you cannot see this text, because on the left there's a request and on the right there's a response for such API, right? So like this slide is just for getting the feeling of the payload for the request. Like request is about 3 kilobytes and response is about 600 bytes. And we receive such information for like where is user from, what's his IP address, and what he's interested in, and so forth. And we need to respond how much would we pay for showing the ad to him. Yeah. So the latency requirements for this API is quite strict. Like it's not an average. Like 100 milliseconds. It's like 98% of the request must be under 100 milliseconds. So if you start replying slowly, you are throttled. And when you are throttled, that means you are losing money, right? So it's better to keep up with this requirement. Yeah, so basically, and we got 200,000 such requests per second currently. As you can see, this is a screenshot from our metrics. So basically, when you have a limit of 100 milliseconds for the response, right? 40 milliseconds is actually dedicated for network latency. That means that 60 milliseconds is left for processing the data and responding to a bit on a server. So this time goes to like deserializing request from JSON, processing some rules. Then you have to retrieve the record from your cookie storage to know what do you know about this user. Has he visited some sites a long time ago or not? And depending on that, you decide the bit price. Yeah, and then when you got the bit price, you just serialize the response. And all must be done in 16 milliseconds. Yeah, so for, as I mentioned, for storage, like cookie storages, we use Redis, Cassandra, and Aerospike, and every has its own niche where it suits best, right? So just shortly about the Redis, we use it as a key value store. We use it because it has great operations on sets. Because in some cases we need to operate on sets and do operations like intersect, union, and stuff like that. It works great, but actually the main flaw is that you must watch out while writing and reading simultaneously on the same node. Like if you write and read at the same time intensively, you can get the latencies like this. As you can see, even it's a in-memory data store flushing to disk every second. You can get the latencies, 99th percentile of the latencies, like up to 1 millisecond. This is really bad. So what we do is we have our slaves configured to be persistent slaves. So everything goes through master, but master just passes everything to its slaves. The slaves flushes down the data to disk, and the data is read from a master. So there's no high latencies. Because in this case, high latencies are caused by blocking, because Redis is a single thread, as you know, and stuff happens like this. Yeah, so let's talk about Cassandra. Are there any Cassandra users out there? This not so many, because it's getting quite popular now. Cassandra is actually a distributed and decentralized database. By distributed and decentralized, this means that it keeps its data ranges on a separate node. It is elastically scalable. I know that everybody knows what scalable is, but elastically, who knows what that means? This means that basically you can scale up by adding new nodes, and when you don't need so much data, or you start losing data, it's not needed anymore. You can scale down by removing the nodes, and everything just goes automatically, which is a really great feature. Yeah, it's highly available because it knows what nodes failed and what nodes are up. It's fault tolerant, tunably consistent, That means you can tune your consistency by some factors. It's a column-oriented database. So why Cassandra is good for us? Basically because of fast writes. We do a lot of user profiling, so everything needs to be written really, really fast. And user profile is a natural key-value module, like you have KD and everything else, right? It's really easy to scale. Just, I don't know, currently it takes like about 10 minutes to deploy a Cassandra ring to a new data center. It's really awesome. And I think we were the pioneers, Cassandra users, because we started using it from version 0.7 like. And Cassandra also runs on legacy Sphere hardware. And actually, when we started with the version 0.7, we also ran it on Windows, unfortunately. And as I said, it runs on a legacy Sphere hardware. This means that you can even have your Cassandra cluster on Raspberry Pi. Yeah, so having Cassandra cluster on Windows is actually the same effect as having it on Raspberry Pi. So deploy it on Linux, don't use Windows, Cassandra. Yeah, and the important fact I didn't mention is that Cassandra is written in Java. So anybody can guess why it can be bad? Yeah, everybody always blames garbage collection, right? But actually, yes, it is. It's not so good because of GC pauses. And when we tuned it, actually some cheap tricks like done in configuration, which helped us to achieve a better latencies, like level compaction strategy. So we have sized tier compaction strategy. Use it when you need fast writes, and level compaction strategy needs to be used when you need really, really good read latencies. Yeah, and at the very beginning we started by running our Cassandra JVMs with 16 gigs of RAM. And basically because we have a lot of RAM in these machines, and we thought that giving a lot of RAM, this would be a great idea because, you know, it would work faster. But actually, by changing our 16 gigabytes of heap size to 8, helped us to reduce the latencies twice. Yeah. And the other winning was while we made a client direct read of data. We switched on a token-aware strategy for our Cassandra client. So basically, why it worked? Because, as you know, or don't know, Cassandra is distributed, and it distributes its data between the nodes. Like if you have a ring, a cluster, a Cassandra cluster, 4-node ring, then it will assign a token to every node, and every node will be responsible for only some range of data. Like, for example, if you want to write a key with the value 10, right? So this key will be written to this node. And if you want to write a key like with the value 80, it will be written to this node. Right? But if you by default use like client like, I don't know, DataStax Cassandra driver, and you want to read the key with the value 10, you might hit this node, and then this node would say, oh, okay, I do not have such key. I do not have such key, but I know who has it. So I might retrieve it from this node. So you have two network round trips, right? Which is, again, really bad for your latencies. Yeah, and actually Cassandra tuning tricks that did not work, like GC tuning, because, you know, if you get a new Cassandra version like every month, it's difficult really to keep up with the updated code and changes made, so it's just useless. Don't do that actually. So, and actually when we deployed our Builder APIs, like using Cassandra and reading cookie profiles from it, we got that 20% of our requests exceeded 40 milliseconds, which, as you remember, in real-time bidding processing is a failure because you cannot keep up with the 100 millisecond latencies requirement. So we needed to do something. So we had a plan, like setting a socket timeout to 10 milliseconds while trying to read from one Cassandra node. If that node like is in a GC pause now, then let's switch to another node, yeah, because Cassandra is fault tolerant, and you can say that, and you can say your application factory. This means saying how many copies of the same data you want to have. So basically, we use a replication factor of 2. We need so this means that we have 2 copies of the same data in each data center. So actually, we have 4 nodes having the same data. So this should work if we repeat this 3 times, like failovering. So yeah, this is just a simple slide, like showing the C# code connecting to Cassandra using Thrift. Cassandra currently now has a SQL protocol, and actually Thrift is deprecated, but we do not use SQL because of our legacy code and how we store data in Cassandra. And actually SQL is just another SQL, and you know, you have no SQL database, but you write SQL range, and you need all the, you need to know all the abstractions, what's happening underneath. So I don't know, Thrift is quite simple protocol, and it's easy to understand how bytes are laid on a disk, you know. So yeah, so and this is example, like I've mentioned about the replication factors and data copies. So for example, this is a table taken from a Cassandra metadata about data ranges. Like if you have a value 10, a key value 10, this means this value would be kept in these 2 nodes, like 197, 198. So you can have a failover reading between them. Yeah, and actually it seemed like a good plan, but it didn't work, like because .NET socket send receive timeout does not work for values like less than 500 milliseconds. So .NET is quite not suitable for low latencies. And it didn't work. The same applies to socket async event arcs, which is a synchronous version of sockets. Yeah, but actually it was even worse because, you know, we tried to implement our own timer mechanism. Yeah, but actually it became too complicated. We dropped that. But we actually found a good old solution, like using POSIX socket API, which is available surprisingly in .NET, and it's socket poll, and you can specify your timeout, which is in microseconds, which is actually awesome too, because this is the only API I know where you can specify a timeout in microseconds, right? It's pretty cool. So actually what a client poll does is like blocks for a specified timeout, it blocks until the specified timeout elapses or you receive the data. So, and it returns true or false. True if the data is available for reading, like, and false if it did not waited for the result in specified time. So this is pretty much simple code snippet showing that. Yeah, and after doing this, it seemed like the plan succeeded. Now we had only 2% of requests exceeding 40 milliseconds. Yeah, but instead of 20. And we could just scale by adding new servers. Yeah. Actually, we had 32 Cassandra nodes for that case. And we could handle with such amount of servers like 150,000 wires per second. But actually we decided to scale by adding less servers and like switching Cassandra to Aerospike DB. Anybody here knows something about Aerospike?
It's some fast key value.
Yeah, it's actually super fast key value store. It's written in C. It works really well with some specified models of SSDs, just like it writes directly through an SSD driver, not by going to a user space. So you get a really super fast performance. It's like Aerospike DB is just like an API higher. It's basically an API for your SSD, and it's also fault tolerant and has all the features mentioned before. And the switching story, like you can watch this presentation, which is done by my colleague Tadas, and he talks about that stuff. And with the Aerospike, just you don't have to do anything. Just you will have already these low latencies with twice less servers. Actually, we run everything on 6 servers now, and 6 is just because we want to be safe. Because of failover, actually we can handle on 2 nodes, I guess, all the load. Yeah, so going to the final slides of my talk, like the takeaways. So don't measure latency averages. It hides really important parts of your system. And unfortunately, usually it's not the case of the GC boss, right? It's just something wrong in your architecture. And it's expensive to scale in network because we have to roll our own Cassandra library, while Java developers having fun with STNX, data stacks, drivers, all the stuff. Yeah, and as I've mentioned, we started with the bidder APIs written in Windows Communication Foundation services. We have rewritten it to HTTP listener. It actually saved about 10% of CPU. But for example, NetBeef framework, the famous Java networking framework, has a throughput like 50% better. And we use Finagle for some of our APIs, which is great. We are very happy with it. And that blocking is not always bad. You need to measure and collect metrics and then do all the final thoughts about that. And you need to choose the right NoSQL, because there's no, like, the best NoSQL in the world is It has some drawbacks, but it has some great features. You know, you need to compare it, and you need to choose what do you need. Thank you. Do we have time for questions?
Yeah, we have like 10 minutes for questions. So.
Okay.
10 минут на вопросы, пожалуйста.
Yep. Yep. Yeah, we just add new servers. And
you also mentioned that you early adoption of Cassandra.
Yep.
So you definitely should have faced the problem when you add new nodes and your Cassandra cluster starts to migrate away.
yeah, and
And
actually,
then the entire cluster gets literally exploded because of that.
not unless you know what you're doing, but it takes time because you need to do special commands and special stuff to migrate it manually, like sitting and waiting, you know, and going around your ring. But the situation is better, and actually it's great now because of V nodes, the virtual nodes, Cassandra features, the feature that was introduced lately, where everything works just automatically. Because the pain, the most pain is assigning new tokens to a new node, right? And you need to do this manually. And with that, the presence of virtual nodes, this is done automatically. So we use that.
Еще вопрос?
About, let's say, type of queries you was using for Cassandra, are you using some kind of index, secondary index, or are you using some kind of your own built-in data structure?
If you need to read your data in some special way, you need to store it like this way. This means we don't create indexes, and if we need to read data by a cookie profile, then the key is a cookie ID, and the rest data is all the rest. But for example, if we have some reporting data where we query it by date ranges, so we choose like a key as a date, right, and everything else as a value. So you need to think how you will retrieve the data and choose how you will store it. There's no writing sequels and joining.
So basically, when you need to update both data, you will actually doing
two writes or 3 or 4.
And second question, there was an image with your infrastructure and there was Hadoop. So how do you use Hadoop?
Hadoop actually is used for calculating the prices based on history data. I cannot actually comment anything more because it's just like have our data scientists and they just retrieve all the data, send it to Hadoop, process it, and send it back, and then we build.
Just because you're using Scala, I need to ask this question. Why you are not using Akka? And for example, I see that you have native. Why not to use Akka IO framework, for example? Because it really, well, according to benchmarks, it actually give you a better throughput.
Yeah, according to benchmarks, but actually, I never read the websites where they compare something to something, basically because you can see, you can make up a benchmark where like Cassandra beats Aerospike, but
right.
So I don't trust them.
What about your experience in this area? Did you try it?
Yeah, we use Akka in some of our APIs, but in others we use Finagle, which is basically not ACA. It's just like basically processing a request in Finagle means you need to write a function which transforms HTTP request to HTTP response, and this is simple. Yeah, and ACA is also great. I don't know, it's just flavor of. You know, we wanted to try it because of all the features like latencies, failover, retry. ACA basically you don't have out-of-the-box metrics, right? You have to do something. Yeah, probably, but you know, we built everything up from a small APIs, like you know, so there might be an API written in Haskell, even if it works and it's fun to work and it brings some value. So why not? There's no such thing like, oh, you should do anything in ACA.
And of course, it's hard to migrate the system to ACA because it have a different paradigm. It's hard to, you know, you need to be a message driven instead of log.
Was your story just an evolution from Redis to, let's say, Aerospike, or are you still using all these systems like Redis, Cassandra, and Aerospike for digital?
Yeah, we use all these systems. As I've mentioned, we use Redis for set operations because if you try to retrieve multiple keys from Cassandra, the latencies would be terrible because it does a multi-get and it just distributes the request and gathers and returns the result, while Redis, everything keeps in memory and you know there's no so much data and everything fits in the memory. So.
And you say that you are not reading the benchmarks.
Yeah.
From a different size.
Quick question on metrics. How do you get like a percentiles across the cluster? I mean, it's easy to measure things and get those percentiles for one process or one instance. And then there is a cluster.
Yeah. So actually measuring latencies and collecting them on a single node is easy. You can keep them in memory. Then we send them to a Graphite. We use Graphite for storing and collecting the metrics. And for visualizing them, we use Grafana. So Graphite is really cool in this. In this.
Еще вопросы?
Have you considered, so I'm interested in the reasons why don't you move into some Linux server to take advantages from Cassandra? I mean not tackling these .NET problems and the lack of driver, but to have some separate systems that works with nice driver.
Yeah. So as I've said, .NET is a better API, but like some of the APIs written in Scala, it uses Java drivers, so it's just you know. Everything was actually, as always, happens because of legacy or historical reasons. So then, when you get the idea how it should be done, you start to.
Спасибо.